Welcome, everybody. Welcome to the backyard. Thank you for joining me on this quick video lesson on thermochemistry. It is nice that you are here. I appreciate you watching this. So this is going to be a new idea, a new concept. And thermochemistry, well, kind of like the name implies, thermo for heat and chemistry. So it's the heat that is involved in chemical reactions. Chemical reactions because when you do a chemical reaction, you're either going to make new bonds or break existing bonds or both. And so every time you break a bond, you need to put energy into this because bonds don't break by themselves. And so you have to put in some energy. And if you remember a little while back, we talked about chemical reactions that take in energy. And those chemical reactions were called endothermic. On the other hand, when a new bond is being made, energy is actually being released into the environment. It's being released by the chemical reaction. And this might be kind of odd to think about, but remember that when atoms bond, they do that and they become more stable. And by being more stable, that means that they have less energy. The more energy something has, the more unstable it is. So when something becomes more stable, it lowers the amount of energy that it possesses in it. Right? Its internal energy goes down. So that's why when a new bond is being made, the energy of the chemicals, the internal energy goes down. And so therefore that energy is being released out into the environment. So you have this sheet here that you can see on the screen. This is in your in your OneNote. This is the W10-1 is your activity for this week. So if you haven't done so, you can pause. Excuse me. You can pause this video and open the file or print it out and follow along with me. So just pause this video, open the W10-1 file, print it, and then start the video again. Okay, so this introduction essentially is just what I've been talking about with you. So it says that during chemical reactions, chemical bonds, the chemical bonds between atoms, are either being broken, they're being made, or both, or some are being broken and others are being made, right? So remember that in a chemical reaction, the atoms don't disappear, the atoms don't appear out of nowhere either. The only thing that's happening is just a rearrangement of atoms. So some bonds are being broken, new bonds are being made, atoms are the same, it's just they're kind of just switching partners or rearranging themselves with each other. So those are the chemical bonds that are being broken and made. Now, whenever energy is being added, this is called an endothermic reaction, right? This is in your notes right here, second sentence. Energy must be, when energy is being added, this is called an endothermic reaction. Also, so this is when you're trying to break some bonds. The energy then, or the energy could be released, right? So a release of energy is called exothermic. So release of energy is an exothermic reaction. Right. So in addition to bonds being broken or bonds being made, there's also an energy play in the chemical reaction because it's not just dependent on breaking the bonds, but chemical reactions require a certain amount of energy in order to proceed. Sometimes it's a little bit of energy and these reactions can occur very, very easily, but sometimes it requires a lot of energy and those reactions proceed rather slowly. So the higher this energy requirement is, the slower the reaction is going to proceed. But there's got to be a little bit of energy there. And this is called the activation energy, right? When you're lighting a fire in the fire pit, the fire doesn't start by itself. you need to start the fire. You need to put in a little bit of energy with the match or whatever it is that you're using, but you need to put in a little bit of energy to get this reaction to start, to get it going. That's the activation energy. So this is that energy barrier that we're talking about, the activation energy right here. And so what we're going to do today is we're going to look at these energies, and we're going to look at diagrams, which are called energy diagrams. And from the diagram, you'll be able to find all of this information: the energy of the reactants, the energy of the products, the difference between the two, and how much energy it takes to get the reaction going. Now remember also that there is a law, which is a law of conservation of energy, the first law of thermodynamics, right? So the energy doesn't, like atoms, the energy doesn't disappear and doesn't appear out of nowhere in a chemical reaction, right? We're always in the context of a chemical reaction here. So if you have a chemical bond, say between a hydrogen and an oxygen atom, and this bond has a certain amount of energy, the bond energy, you need to put that much energy to break the bond. And when the bond is made, you get that exact same amount of energy back. So it's the same process, but it's in reverse. And so therefore it's the same amount of energy. So if you want to break that bond between the H and the O, you're going to put in some energy. And when that bond is being made, it's going to release an amount of energy, which is exactly the same. So always the same amount of energy. That is the first law of thermodynamics. So here is one of those energy diagrams that I was just talking about. You see, it reveals, well, first you have the energy of the reactants, right? So this is the internal energy of the reactants, how much the reactants have within the bonds and whatnot. So it's 200 kilojoules of energy. According to this diagram, the energy of the products is 100. So the products have less internal energy than the reactants. What that means is that the difference between the two, the difference between the reactants and the products, so the heat evolved, right? This drop between the reactants and the product, this is known as the delta H. It's the heat of reaction, also called the enthalpy of reaction. So the enthalpy of reaction is the difference between the energy of the products and the energy of the reactants. So in this case, we have the energy of the products, which is 100 kilojoules, and the energy of the reactants, which is 200 kilojoules. So 100 minus 200 gives you minus 100. That's the heat of reaction. The little negative sign, the minus 100, is important because that tells you that it's an exothermic reaction. So every time the delta H, the difference between the heat, is negative, that's an exothermic reaction. So this is what this paragraph here is talking about, right? So the enthalpy is a measure of the internal energy. And what we're concerned about in chemistry is the difference between the energy of the products and the energy of the reaction. So what we want to know is how much energy do we need to put in, or how much energy is going to come out. So what we're interested in is the delta H. Delta, that little triangle, means the difference. And so energy of the products, according to the diagram here, is 100 kilojoules, right? Generally it's kilojoules per mole. And the energy of the reactants, minus 200 kilojoules per mole. This is going to give us a negative 100 kilojoules per mole, right? And this negative sign right there, this tells you that it's exothermic. So here's both scenarios again. An exothermic reaction, which is what we just saw. An exothermic reaction is represented in diagram B, where the reactants have more energy than the products. And when the reactants have more energy than the products, what's going to happen is there's going to be a release. The energy is going down, right? There's going to be a release of energy. When you do products minus reactants, you're going to get a negative number. The endothermic reaction is the other situation where you actually are going to put in more energy. Right? The reaction requires energy. And so that means that you start at the reactant level, and then you add some energy. Oops. You add some energy to the reactants, and then you get to the products level. So your delta H here is positive. When you do the energy of the products minus the energy of the reactants, you're going to get a positive number because the products are higher. So whenever you get a diagram like this and you need to identify if the reaction is endothermic or exothermic, just look at the reactants and products. If the products are higher, it's going to be endothermic, like in diagram A. And if the products are lower, it's going to be exothermic, like in diagram B. Remember that the equation is always products minus reactants, right? And that is the equation for your delta H, products minus reactants. The activation energy, now that's the energy that we haven't talked about yet. So the activation energy, that was that match in lighting your fire, right? It's that little bit of energy that you need to put in to get things going. Hence the name activation energy. It activates the chemical reaction. It gets it going. That number comes from the little bump or the large bump, depending on the reaction, that you see between the reactants and the products. So in this case on diagram A, what you have is a very small bump, right? It's just like a little speed bump. It's going to be easy to go over that. That's the activation energy. So you start the reactants at a certain amount of energy, and we could call that, I don't know, let's call this like 150. And you need to add maybe like plus 10, right? And that's going to get you up here at 160. And then you're going to go down all the way to your products. So this little bump, this little plus 10 there, that's your activation energy. So you have the energy of the reactants, you give them a little bit, and the reaction goes. In this case, diagram A, it was a small activation energy, right? It was a small amount of energy that you needed to get to add to the reactants to get them over the hill. But there's a very big difference between the reactants and the products. Now, don't get the two confused, right? The activation energy is just to get the reaction to go. The heat of reaction, the enthalpy, that is independent of the activation energy. It's the difference between the products and the reactants. So the activation energy is not part of this. And the reason for that is because if you look at the diagram, the little part that goes up is coming back down. So that little bit of that 10 units of energy that you put in, you get right back. You just have to put it in, and then you're going to get it back, right? So this activation energy here for an exothermic reaction, you add 10, you get your 10 back, and then there's a difference between the reactants and the products. So when you have an exothermic reaction like that, the delta H is the difference between the reactants and the products, as always. And in this case, I don't know, if we put in the products at maybe 30, let's just say. So the delta H in this case is energy of the products, 30, minus energy of the reactants, 150, and it gives us negative 120 kilojoules. Negative sign, exothermic. In diagram B that you have over here, there's a very large activation energy. So the reactants, which are, if I keep the same scale here, the reactants would be maybe at 50, right? But the peak here was at 160. So it's pretty difficult to get the reactants from 50 all the way to 160. So in this case, the activation energy is 110 kilojoules. So that's a lot more energy that you need to put in to get this reaction to go. So generally speaking, reactions with high activation energy are slow reaction. We were just talking about rates previously, right? So it's going to be very difficult to have an effective collision because the activation energy is so high. But like in the previous case, you put 110 in, you get 110 out. The heat of reaction is just the difference between the reactants and the products. In this case, delta H is equal to the energy of the products, which is 30, minus the energy of the reactants, which is 50, and you get minus 20 kilojoules. So a lot less energy is being given off by this reaction. And this is how you interpret the graphs. This is the beginning of your activity here, where you have a graph, and you simply have to put in the correct terms, like for 1 to 9 over this graph, and use these as a guide to help you. Once you have completed this little kind of fill in the blank, I've included for you a online activity on the University of Colorado, which is absolutely fantastic, on the PHET, P-H-E-T, the PHET website, on reaction rates and bond energy. Again, thank you. This was just, like I said, a quick lesson on bond energy. Hopefully it clarifies a few things and helps you to move on in thermochemistry. Thank you, and have a great day.